In today's lesson, we're going to be solving trigonometric equations. In our first equation here, we want to solve 2 cos squared x plus 3 cos of x is equal to -1. So in this question here, they've bounded our x value, bounded our input between 0 and 2 pi. So like any equation that we want to solve, you're going to want to bring everything to one side and try to factor this equation here. Now, bringing everything to one side, we make the following observation. You'll see here we now have ourselves an equation that is in the form of a quadratic. So if we take a look here and we view this as 2t squared plus 3t plus 1 equals 0, if we were to factor this here, we can go ahead and do charting on this, or decomposition, whatever you prefer. So I'll do the factors of 2, factors of 1, and we see here going through charting, this will factor quite easily into t plus 1 times 2t plus 1 equals 0. But again, this was not a t, it was actually a cos of x. So therefore, our original equation that we were looking to factor will factor into the cos of x plus 1 times 2 to the cos of x plus 1, and that's equal to 0. So now we're in a situation where we have the product of two expressions as 0. The only way that can happen is either the cos of x plus 1 is 0 or 2 cos of x plus 1 is 0. So solving for these here, we get cos of x is -1 and -1/2. Now, on our unit circle, where is the cos of x equal to -1? That's going to happen right here, and that relates to an x value equal to pi. So therefore, when x is pi, we have here the cos of x is going to equal -1. Let's take a look at our unit circle for cos of x equaling -1/2. So you'll see here the cos of x equals -1/2 in two quadrants here, this quadrant here and this quadrant here. Taking your cos inverse here, you will find the value of x that you get here are two values of x. You get x is equal to 2 pi over 3 or 4 pi over 3. So again, this is one complete revolution around the circle. So we have our three values here. These are our three answers to this. So the equation is going to be 0 either when x is equal to 2 pi over 3, 2 pi, or to 4 pi over 3. And again, that'll be a true solution, one complete revolution around the circle from 0 to 2 pi. Let's take a look at another example. In the next example here, same idea. We want to be able to solve this trig equation. So we're going to bring everything to one side of the equation. Doing so, we can now quickly make the observation that we do have, in fact, a quadratic form here. So treating this tan of x as just a variable, let's label that variable as a t, we end up getting 2t squared minus 3t minus 7. Going ahead and factoring this, So going ahead and factoring this here, we end up finding out that the roots of this quadratic are irrational. So I went ahead and calculated the discriminant. I did not get a perfect square, so using the quadratic equation and collecting to two decimal places here, we end up getting t values of 2.77 and -1.27. Now again, that t was actually a tan of x, so we end up having the tan of x is going to equal 2.77, or the tan of x will equal -1.27. So at this point here, we can express our answer either in degrees or radians. Let's go ahead and express our answer in degrees this time. And again, we end up getting two values here. One value here, x is equal to 70.15. And then the other location where tan of x is equal to 2.77 will be your x value of 70.15 and then plus 180 degrees, giving us our second answer of, so either x is equal to 70.15 or 250.15 degrees. Now let's take a look at what x values we get for -1.27. Taking our tan inverse, So go ahead and taking our tan inverse here, I get two values from my calculator. My calculator had outputted the 308.22 degrees. That would be this value down here. Now again, tan of x is going to be negative in this quadrant as well. So what I did was I subtract 180 degrees to get me back in this quadrant, giving me 122.22 degrees as well. So these four answers here represent the four solutions such that our quadratic equation here is equal to 0, i.e. solving our trig equation. Let's take a look at another example. In the next example here, we want to solve here for our x value here. Again, like most strategies, you're going to want to go ahead and first get rid of the roots as much as you can, write them in exponential form. Doing so, And again, we want to go ahead and solve for x. Before we do that, we have to solve for tan of x. So I'm going to square both sides, giving us the tan of x is equal to x to the power of 1/2 this time. And now you can take a look here. If we go ahead and write this in a form you're familiar with, this becomes the tan of x is root 3 Quickly looking here, we can go to our unit circle, and this gives us x values equal to. So I'm getting x value equal to 60 degrees, so that's going to be all the way over here. And this will be our x is equal to 60 degrees. And therefore, the only other location this would happen would be in this quadrant here, in which case, again, we can add 180 degrees to that, right? That'll put us in this quadrant here. And doing so, we get 240 degrees. So the two answers to this equation here will be 60 degrees and 240 degrees. Now, one thing we have to watch out for is we did square both sides of the equation, so it could be the case that we introduced the option of extraneous root. So let's go ahead and check our answer by substituting both of these answers into our equation. And you can see here quite quickly, substituting either 60 degrees or the 240 degrees ends up yielding the fourth root of 3. So we have found both solutions. Let's take a look at another example. For the next example here, we want to solve this trig equation. Now you're going to notice here in this situation here, we have the cos of 2x and the sine of x. Now some trig equations, you have to use your actual trig identities. So in this case here, you'll notice I have the cos of 2x, and I have 3 different formulas I can use for this. Well, based on the work we've done above, you can see that having the cos of 2x expressed as a function of just sine of x would at least give us the opportunity to use the quadratic equation and do some factoring. So I'm going to replace the cos of 2x with 1 minus 2 sine squared of x, and then we have our sine of x from before equaling 1. Simplifying and factoring, we end up getting here negative sine of x times 2 sine of x minus 1. And again, the only way this can be 0 is if these two equations are 0. Setting each factor equal to 0 and solving, we get. So going ahead and solving, I end up getting here the sine of x is 0 or sine of x is a half. Well, sine of x is 0 at 0 and pi, and sine of x is a half at pi over 6 and 5 pi over 6. So putting our answers together here, we're going to get solution is going to be at 0, pi over 6, 5 pi over 6, and lastly pi. So this is an example of using your trig identity first and then proceeding like we did in the previous examples. Let's take a look at another example. In the final example here, we want to take a look at the following. We want to solve this trig equation. In this one here, they want you to recall your compound angle formulas, and we make the observation that the sine of x minus y, if you recall, is equal to sine of x cos of y minus sine of y cos of x. That's exactly what we have here. Your x here is going to be 5 theta, and your y here is going to be 2 theta. Therefore, this expression on the left-hand side can simplify to become the sine of 5 theta minus 2 theta is going to equal root 2 over 2. Simplifying, we have sine 3 theta equals root 2 over 2. Let's go ahead and take our sine inverse here and solve for our angle 3 theta. All right, going ahead and taking the sine inverse here, I end up getting that the root 2 over 2 happens at your 45 degree measure and when theta equals 135 degrees. Going ahead and dividing across by 3, we end up getting 15 degrees and 45 degrees. Now we want to take a look at what is the period of the sine of 3 theta. Well, your normal sine function has a period equal to 2 pi. And now what we're doing is we are compressing this by a factor of 3. So we're going to divide that by 3. In degree measure, this will end up being 120 degrees. 2 pi over 3 radians is 120 degrees. So therefore, we're going to go ahead and add the period of the function to each of these values and keep adding that until we use up our entire space here, right up to 360 degrees. So doing so, we get the following. Going ahead here, we have our 15 degrees and our 45 degrees. I went ahead and added the 120 to the 15. I got 135. Added the 120 to the 45. I got 165. Added the 120 to the 135. I got 255. And added the 120 to the 165. I got 285. So the answers here are 15 degrees, 45 degrees, 135 degrees, 165 degrees, 255, and 285. You'll notice if I add the period of the function again, we'll be outside of the domain of this equation. So this becomes our solution set. All right, that concludes today's lesson on solving trigonometric equations.